We're just saying I was.
Hi everyone, thank you very much for attending our seminar. Please join me welcome our seminar speaker, Dr. Ghulam Rasool. Dr. Ghulam is assistant member in the Department of Machine Learning at Moffitt Cancer Center with a secondary appointment also with the Neuro-Oncology Department. He also had an appointment with the Electrical Engineering Department at the University of South Florida. Before Moffitt Cancer Center, Dr. Rasool was an assistant professor at Rowan University, where we first met and we were working on, this was our first project on NSF I4 project, where NSF fund scientists to explore the commercial potential of their technology that are developed in the lab. So it was our first collaboration where it was a very challenging and rewarding experience working on not only the scientific part of the research, but also on the business part of it. And later we had like a contract with Lockheed Martin for a project for a year. And even after moving to different institutions, we're still collaborating on multiple projects. And Dr. Rasool research focuses in multimodal machine learning for cancer diagnosis, treatment planning, and risk assessment. He has numerous funding from NSF and NIH, and he recently got an award, Junior Researcher Award from Moffitt Cancer Center. So please join me welcome Dr. Rasool for our speaker today. Yes.
Thank you so much. And, I greatly appreciate giving me this opportunity to talk about my research. I think people can hear me. No, you cannot. Okay. Should I be louder? Now it's better. Oh, okay.
It wasn't coming through the Zoom without mic. Sorry. I guess worst case, people can move on closer to the front. If you can't hear, you can always grab a seat up front. We can hear you online.
Okay, and are there any other mics that I can use or? I think this did not work. Yeah, not now.
But we could try the lapel mic again and see. I don't know what's wrong. Maybe
Okay.
this will definitely work in the room.
Okay.
So it just wasn't online. So do you want to put that?
We'll have to change that here.
Yep.
Oh,
Do you want to try and see how people can hear?
so can you hear me now? Okay, that's better.
Zoom, and then this should work in the room. I hope.
Okay.
Yes.
Yeah, we can.
I'll go listen and make sure.
It's much better now. Okay, perfect. Okay, so my background is in electrical engineering, but then I went to a cancer center, which is a hospital actually. I do have courtesy appointment or just appointments in an academic appointment in university, but my main focus is research in a cancer center. In a cancer center. So let's talk about cancer. Cancer is a broad term for diseases characterized by abnormal cell growing uncontrollably. These are cancer cells are part of our body, but they refuse to die. And they start invading other parts of the body. So it's not easy to target them because they are already part of our body. These are some of the statistics, and these are very well-known statistics that cancer has become the leading cause of deaths in the world, around 9.7 million deaths. and there are certain risk factors associated to cancer. So early detection of cancer is one of the areas where people focus on, because it's well established that if we can detect cancer early, we can have better treatment outcomes. And when we talk about the treatment, unfortunately, we are standing at a place where we were more than 50 years back, which is we'll try to resect the tumor. Talking about the solid tumors, we'll try to resect, physically cut it out and throw it away, or we'll do chemo, which means that we will systemically give different chemical to people so that we can kill all the cells that are reproducing fastly, and that's why many people lose their hair, because those are the cells which are rapidly dividing. And the third one is or radiation, where we'll try to use radiation and try to kill the tumor, and that's where we are. There are some therapies which are being developed, and immunotherapy is one of those. But we need a lot of more efforts on the data side before those therapies can be actually effective for a larger set of population. So with this background, let's try to see that when people who are more on the quantitative side, when they talk about cancer, what type of data we are talking about. We are talking about the tabular and categorical data, and that data may be coming from demographics of a person, because we know that certain cancers affect certain demographic groups more than others. Same is true for genders. So that's a good information to have for when we are talking about making various predictions based on different machine learning models. We also have clinical data, which means that stage of the cancer, grading of the cancer, different labs like blood work done, BMI of the patient, and several other data points. Molecular data, which may include some information about genetic disposition of a person, which makes them at more risk for certain cancers. We will have imaging data, which may include radiological data and pathology data. Radiology will include CT scans, MRIs, mammograms, PET scans, and other data. Pathology data will include digitized slides from tissue that is physically extracted from the cancer site. And then the text data will include surgical pathology reports, radiology reports, clinical notes, patient-reported outcomes, and many things. So the idea here is that when we are talking about cancer, we are talking about something that is inherently multimodal. People have been trying to address unimodal approaches, but of course, they will not be able to tackle that because the phenomena is inherently multimodal. And the way that we have been collecting data about it is multimodal. So let's use multimodal models to address this. So with this background, actually, I wanted to give you a quick overview of how I'm going to present some of the work that my lab has been doing in the last 2 years since I joined Moffitt. We'll briefly talk about large language model and how we are trying to use large language models, and then we will go to VN language and multimodal models, and finally, foundation models and something about applications in cancer care. Yeah, I should keep track of the blame also. So perhaps many people have heard of and they may have used ChatGPT type of models. There is a lot of engineering around language model that is done to make it sound like something that you can talk to. But at the end of the day, there is a language model, and language model is nothing more than predicting the next symbol actually. But there's a lot of engineering, so it feels different. But from machine learning perspective, given the previous context, these models are predicting the next token. They are large because they have huge parameter space, and we use trillions of tokens to train them. And if you want to really train these models, you need millions of dollars actually, but you may be able to do some better things with those millions of dollars. So take vacation or retire early. So, but some people actually go and train these large language models, and they have. And one of the key ingredients is, apart from data, one of the key ingredients is actually GPUs. And most of you must be familiar with how hard it is to find these GPUs these days, even if you have money. So, so throw in a lot of data and GPUs, and you will get large language model. These are some of the steps that we actually do take to train these large language models, which is collect massive data from internet and do some pre-training. People may do some data labeling also for supervised fine-tuning, or what they call SFT. Later on, there is some human preference also introduced in this training, which is usually referred to as RLHF, reinforcement learning based on human feedback. There is some instruction tuning going on, which means that we want our model to understand some of the instructions that we pass to that model. And this is especially true for chat-based models. And finally, local fine-tuning, which perhaps is more relevant to some use cases that we have inside Cancer Center, where we want to use those models that were trained on public data sets to be able to work for our specific use cases. In general, it's a very vague, but still gives us some sense of how much time and money people spend on training these models. Most of these models are being developed by either very large technical companies, you know them, and or some startups which are backed by a lot of money. But at the end of the day, these models are next token predictors. And there are some models which are available in open source space, which we can leverage for our own use cases. So just quick overview of these models. Do not process, of course, they don't process words. They cannot process words. The words are converted to tokens. Tokens are converted to numbers, embeddings, and then embeddings go into the model. Just like the images, we have RGB values or some other representations which are actually fed to the model. This tokenization is a challenging part of these large language models, because this example, I stole this example from Andrew Yang from one of his lectures, and the idea is simple, that if you want your model to reverse the characters of this word like chemotherapy, the model won't be able to do that. A human can actually do that very quickly, but model won't be able to do that. And the reason is simple tokenization, because our models do not process characters or words, they process tokens. And why we do that? Because that's the most informative, from information perspective, that's the most efficient way of processing data. So if the model does not have chemotherapy as one of the words in its dictionary, it's not going to process that as one word. So we will have, this model is not, is perhaps going to struggle a lot if you try to teach this model, or if you try to extract this from this model on some, do extraction on some data set using this model that includes words chemotherapy or radiosurgery or some of these words. And that's the reason when we are trying to use these language models internally on our data sets, which may have these words, either we have to make sure that these words are part of its dictionary, or we have to go back and work on the dictionary of the model before we can use it. Very quick history, it's going crazy. There have been many models proposed in the last 4 months, and keep on coming. I think 3 models came in the last week: Phi 3, Mixtral, and Llama 3, and it's keep on getting worse actually. So, it all started in 2018. It did not start in 2018. There were people who were working on attention mechanism. There were people working on NLP for decades and decades, 1950s, 60s. But some people put together some concepts around the transformer models in 2018. I think 2017 or 18, they were using the attention, which was again already proposed. They used the concept of embeddings, which was already again used, positional embeddings, which was already proposed and used. And they were able to process NLP data more efficiently in parallel. And the way that I think about it is that when we were using LSTMs or GRUs or other more classical models, we were limiting ourselves to processing one token or one piece of information at a time, which was limiting ourselves because we were not able to use parallelization offered by the GPUs. What transformers did was they gave us a way to package the sequential information into the data itself, so that now when the data comes to a transformer processing, that data already gives you an information that, hey, I am the third in the sequence. So you don't have to process that data third in the sequence, because the information about being third in the sequence is in the data. So you can process all the data at once. And that allowed us to use GPUs, and that changed everything actually. And one of the first models that used that was BERT, and then GPT-1, and now the things changed actually in last 5 years. From GPT-1 to we have GPT-4 and many other models that are doing much better than any other model that we have ever developed. So what are large language models good at? They are good at doing some things, maybe less of a thing, and they are bad at doing many things. But from my perspective, from our lab's perspective, or from cancer perspective, there are certain things that we can use these models for. And before we can do that, we have 3 different types of training, 3 different ways to tame these models, which have already been trained or being trained. The first one is model training. Again, these are standard machine learning strategies, but we don't do that. We actually do the second one, which is adapter training. Adapter training means that I take the same model which is available online in the open source domain, like Llama 3. I'll take that model, download it on my computer, and train an adapter for that model. Which means that the same, when I do inference on this model, I'm going to use the same model, but with a small adapter. And that adapter allows me to fine tune the output of this model for very specific cancer use cases. And I'm going to show that in the next few slides that what my use cases are. And finally, the third one is prompt engineering, where you just keep on adding more text to your context so that the more you try to give model a better context to make a prediction which you expect it to give you. So, but here is a challenge. All data, all hospital settings or any settings where there are concerns about data privacy, and banks are also included, many other organizations are included. We cannot just use any model or any company's APIs which are available on internet, because we cannot share the data. Even I cannot see all the data that is available for 700,000 plus patients at Moffitt, because I don't have that clearance. I need to have certain regulations and certain regulatory approvals before I can see that data. So how do we process those data sets using these models? We have to run these models locally behind our firewall at Moffitt. And the challenge is that on the right-hand side, if you see 7 billion times 4 bytes, that's a 7 billion is perhaps one of the smallest kind of models on the spectrum of large language models. And I need 28 gigs of RAM to just load this model. Once I load this model, I will bring in my input. Then there will be multiplication between input and my model's weights, and the output will be activations and everything that's on the top of this, even for the smaller models. So this is inference only, not training. So we need some easier way to make this model more efficient at inference time. And that's where some of these approaches help us. We can do model quantization. There are some ways, for example, GUF is one of those ways, GGUF. There are some libraries that can help us do that. And at the end of the day, I can run this maybe 22 billion parameter model on my desktop computer, which has a 3060 GPU with 12 gigs of RAM, which means that I have similar capabilities as ChatGPT 3.5 in my local desktop. And now I can use it for certain use cases that I have been. And these are some of the use cases that we have. My lab is developing, is exploring how these models may respond to certain queries by cancer survivors. We also want to work on radiology reports. There is some work on pathology reports. We are working on tumor board and some clinical trial and patient matching. These use cases may not be very familiar with many people here, but I'll try to give you some sense of how we are trying to do that. As I mentioned that most of these models are being trained using data from internet, but the internet is not the best source of information for many real world kind of advices, especially when it comes to cancer, because there are studies which showed that a huge amount of information, especially shared on the social media sites, is actually dangerous because it can prevent people from taking certain actions or motivate them for inaction. And that is harmful information actually. And if I go ahead and just download the data from internet and start training the models, that information is hidden in these language models somewhere. So we have to find a way that we can actually go and explore these models using different questions that cancer survivors may ask or cancer patients may ask these models, and kind of give them the right guideline that just as social media is not the right answer for cancer related questions, just as Google is not a doctor, these large language models or the chatbots are not the doctors. You don't have to, you should not trust them. Or at least we should have some quantitative measures to convince people that this is not the case. That's where this study is. Second, I hope that you never have to deal with radiology reports, but if you have ever to deal with radiology reports or any other medical text, it's written in an alien language, actually. I don't know why they do that, but that's what they do. And that's not only challenge for patients, that's challenge for the other physicians also, because physicians complain about physicians that this is really hard to read report, or this report is too long. I don't have time to go over 10 pages because I already know the patient. All the record is there. All I need is a very specific information on what's going on, so that I can go ahead and spend my time on something that is better than just reading those 10 pages of those reports. So that's where we are trying to use large language models. And we are trying to, this is an example case where we are trying to take the text from the report and generate a report for the patient also, which makes sense for them. And for physician also, physician does not need all of those things. They all need just a simple and more quantitative and more informed words that make sense to them. This is another example of chest X-ray before and after, and these reports have been verified by the radiologist, and they think a set of radiologists, and they think that these language models are doing a good job at squeezing these or making these reports more concise. And this study is this study is now, we are doing this study right now. So we have, I think I have some results more recently. This is another example where we were able to squeeze a 386 words report to 114 words. And these are the now 22 different radiologists who are part of this study. And this result shows that if the radiologist is on the top, they are producing concise reports. And if they are on the bottom, they are not producing a concise reports. So again, this study is still under progress. We are giving this feedback back to radiologists. Some radiologists like it, some hate it. And that's going to be the case for any technology. Some people like it, some don't like it. But the idea is not to judge them. The idea is to provide them feedback that if they want, if they like, they can make their reports more concise, write less words, read less words, focus more on something that seems to be more useful. Instead of writing 10-page report and you know that nobody's going to read that, and you have a lot of redundant information which is already available in different places for the same patient. This is another use case where we are trying to extract certain words from from surgical pathology reports. It sometimes feels strange, but it's fact that right now, the way that most of the data for cancer registry is collected is manual, actually. So we hire people, hospitals hire people who are called cancer registrars. They sit down and they go through the clinical notes, reports, everything manually, page by page, and then extract the type of the cancer, characteristics of the person, type of the type of the treatment that was given, and have all the information manually from those. And then the data goes to a second registrar who is going to confirm everything. It takes 6 months and thousands of dollars actually to process one record, which is obvious because you hire people who sit down and spend hours going back and forth between the nodes. And what we have been trying to do is use large language models to extract first set of variables so that people can just look at those, go back and see where the text was extracted from, and then sign off. And these are some of the use cases because these files are always stored in the PDF format. So our language, our solution, it will go. It's easy these days. There are tons of OCRs actually available. And you run the OCR, you have the text, feed it to the language model. It's going to extract very specific information in JSON format, and then share that information with the registrar.
A very short question. What is the rate of mislabeling when human makes mistake in processing?
For human registrar, we are at 90%.
19?
90%. So there are two levels of human registrar. So the first one goes through all the data. They write these variables that's what they think that histology is endocrine adenocarcinoma, NOS. And then the second registrar is going to come in and verify this, if this is correct. After the second, the accuracy is 90%.
So 10% mistakes.
There are still 10% mistakes which people think exist, or when they go back and and it's 6 months actually. That's actually because this means that the patients who are being treated today, their records will not be updated till next 6 months actually. So if you are doing some cutting edge research, you are developing some therapy based on the current data, you won't be able to do that. You are able to see that till the time that that data is updated. And we are developing that. Again, this project is a development. We are still developing that, and there are other use cases also. So that was the first part, which was kind of how to use large language models, and again, fine-tune for our internal use cases, run inside Moffitt's firewall. No public use. We cannot expose our data to any public APIs. The second part is more on the multimodal, where we want to see that if we can use multimodal for our use cases. So many of the people here in audience are familiar with this. We have seen a lot of work in classification, detection, segmentation. These models seems to work very well. But there was some work from OpenAI, which is called CLIP. And this was perhaps one of the early works that showed that we can talk about joint feature space or embedding space where text and image can understand each other. Which means that if I say leap of curiosity, this image will be generated, or if I give this image, the leap of curiosity will be generated. So it's a kind of a space where image and text, when represented appropriately, can understand each other, can be translated into each other. And if I am sitting in that space, I can ask the model to give me given in the same space, given same set of embeddings, I can go and based on some distance metric and kind of find other images or other text actually, which are close to this actually. If you see all of those, this image, leap of curiosity, that image, whimsical pursuits, they are very close to each other in some space. So these are two very different modalities. One is based on vision, the second is based on language. They have nothing to do with each other if you really think about it, but they are being represented in a space where they are close to each other. So the idea is, can this be done for other use cases? And if you kind of think about the images that I showed you earlier, where we were trying to collect different data modalities, different data types from cancer, will we be able to build systems that can see radiology images, pathology, patients' demographics, and they know that we are talking about the same patient? So that's the research that excites me, and that's what I want to do for my research. But before we go there, the most amazing thing which actually kind of excites me is that we have a big, if you think about vector spaces, we have a big vector on one hand, we have another vector on another hand, and they all can talk to each other in some space. And we want to build that space for cancer also. People have done that there are some models from, I think there is a model from a LNAI Institute, which can actually understand 4 different modalities. So there is some work actually. But we want to do that for cancer. And that brings us to foundation models. And if you think about the foundation models, ideally, the foundation model should be able to process all different types of modalities that are related to your problem. But if the problem is only language understanding, then the large language models are also foundation models. So the consensus which the community is developing around the term foundation models is these are the models that can serve as a very good starting point for doing many different things, for answering many different questions. So instead of everyone going back and building their own models, they can start with something that will work for everyone. And they can understand, they can process different types of data and answer many different questions based on zero-shot learning, few-shot learning, and fine-tuning. And here is what I just alluded to, that instead of developing a traditional machine learning pipeline where we identify a problem, collect as much data as we can, and then train the model, let's not do that. Let's start with something like this, where we already have some trained foundation models available. Just like I mentioned that we have large language models, Llama 3 is already available in public domain. I'm going to download that model, fine tune on my local computer for my specific use case, and then use it. And that's what the idea of all foundation models is, that they should work in some use cases for zero-shot learning, few-shot learning, and if not, I'm going to fine-tune that. But I don't have to go through the painful process of going back and retraining everything from scratch every time for every problem that I have. So now comes the real question that we have been trying to, my lab has been trying to address, is actually, can we do that for cancer also, where the data can be clinical records, and clinical records will include all the different information about the patient, like their history, clinical history, their radiology reports, pathology reports, their labs, or any test that the doctor is doing. We have radiology imaging, which we can be MRI, CTs, anything. And then we have histopathology images, which is the digital image of the sample from the tissue. We have molecular data, which is a whole beast in itself. Can we build models that can actually consume all the information and then answer some relevant questions. And if you think about it, the doctors are actually doing that. When doctors plan on, when an oncologist is planning to put a person on a specific treatment, that's what exactly they are doing. They will have them do certain tests, for example, some type of imaging, and will have a radiologist write a report on what that imaging is showing. They will do, they'll get a biopsy of the tumor, and then have a pathologist write a report on what that looks like. And they'll do some molecular testing, and then they get a report from the pathologist. And then they'll sit down and see that, okay, what is going to be the most optimal treatment for this person? And those are some of the questions that they are trying to answer actually. What's going to be the better clinical outcome for this person? Is this person going to respond to this therapy or not? If I put this person on this clinical trial, their chances of surviving are going to be, in next 5 years, are going to be 90% or 10%. Post-treatment surveillance, is this person going to suffer from chronic pain after this treatment? That's what happens in most of the chemotherapies. Not most of the chemotherapy, but many of the chemotherapy survivors, if you go and talk to them, they suffer from chronic pain. If we can predict that this is what is going to happen, we will have a better way of managing that patient right now. And all of this data is available. I'm not talking about the new data collection. I'm not talking about the new sensors. I'm not talking about anything. All we want to do is take all the data which is already available in clinical settings, build models that can process that data, and then help clinician with the better predictions. Nobody is getting out of the business. Nobody is getting out of the job. All we are doing is making them more aware of what choices are available and what choices made. Just like when people invest in stocks, they try to get all the information possible about that company, about what's going on, and how much money should they put in that stock. That's what we are trying to do here, is give them all the information that is available from different sources and better predictions. So they can actually say, okay, yeah, that's what is most relevant for this person. So that's the VN part, but how do we execute it? Because there are many barriers actually. And I have spent last 2 years building these type of models. There are 3 main steps of building these models. The first step is getting access to the data. Because in hospitals, the data is not collected for machine learning. It's collected for billing. That's where this whole, the digitization was done, because they can bill it. Or when they bill it and they are being asked questions, they can come back and show that what treatment was done. So, and now when machine learning has started coming in, so we have started that discussions that, okay, yeah, you are collecting data, but you need to change your data collection processes, because this data is much more than just billing data. So that's the first part. The second part is, between every data set and machine learning model developer, there is a physician sitting, because I don't know how to interpret CT scan. So I don't want to blindly build a model to process CT scans. That's blasphemy, actually. That's not right way to do that thing. Pathologists, they spend whole of their lives actually looking at those slides. And the way they do that is they physically look at the tissue and identify the cells and count those cells. So there is no way for me to actually build blindly some models that will process those images. There is no way actually. It's a recipe for failure. And so that's what I said, that between every data set and me as a machine learning developer, there sits a domain expert that helps me that how you are going to process this data and what answer that you should expect from this data, which is information is there in the data. So go and work on your model so that you can extract that information. And this is the last part, is the easiest part, which is actually building models. So, and the question can be, for example, the question that we are trying to answer for one use case is how long the patient is going to survive, given all of their characteristics, their clinical data, their radiology report, their surgery report, their omics clinical, their genetic disposition. If you give me all of the information, I'll try to predict that how long that person is going to survive. And we divided this into 3 parts and we started 3 different projects. The first one is Minds. This project is complete. We published a paper also, and we have shown that we have ways to, we have built a system that can query different databases, because radiology images sit in a different database, pathology images sit in a different, physically different database. Electronic health records sit in different database and they don't talk to each other. So we have to go and collect data from all those databases and bring together at one place. That's the first part. Second part, again, the pre-process those data sets in a way which makes sense to domain experts, and then build machine learning models. So the second and the third are under development. It's going to take us maybe 5 more years to actually complete all of those tasks. So this is Minds, which is collecting data, and it's already published work. The GitHub repo is also available, where we are sharing this publicly. The idea is to query different databases and then build a single repository for machine learning, actually. This is still the same part. And this is the second part where we are trying to use the domain experts' knowledge and pre-process data for later machine learning. And one thing that we are trying to do is that it's not easy to understand what different types of pre-processing techniques are appropriate for the data based on the nature of the data. So we are trying to get those embeddings and make them available on Hugging Face, just like any other different models, so that if somebody like you, like me, they want to experiment with some cancer data, multimodality, they can just go to Hugging Face, download those embeddings which represent a good information from those very specific data set, and they can do experiment with multimodal model development, not to get lost into the modality specific data nuances. And the third part is actually the model building, and we are doing that in parallel. These are some of the publications that we recently did. These are not full-fledged publications. These are just abstracts because we are actively building that. This is another model which we built actually. This model uses hierarchical graph neural networks, and it's a multimodal model. It's based on the same embeddings. It uses embeddings and tries to predict the overall survival of the patient. Senmo is a model that we are developing to process 6 different molecular modalities. Now, as I mentioned earlier, molecular modalities are a beast in itself, actually. So when we talk about molecular data, we are talking about 6, 7, or 8 different data modalities in itself. and everyone is representing a different feature of the genetic data, which is not easy to pre-process and not easy to, because it's very noisy data and it's not easy to pre-process, not easy to understand. It took us actually, our lab actually 2 years to build this first model, because we don't understand, and this model is still under development. Hopefully in the next few weeks, we will be able to share this model also on GitHub. These are the different types of cancers and the different types of data that we are using. This shows the performance of the model, that if you use 6 modalities as compared to 1 modality, you get a model that has these are the 2 test accuracies. You get a better test accuracy and you get less variance in your predictions. You can extend the same for all different cancer types. So this y-axis represents different cancer types. I'm going to go quickly on the next few slides and kind of leave some time for question answers. Very quickly, cancer cachexia is a metabolic syndrome, and the importance of cancer cachexia is that many people in the community, including our physicians, we don't, as a community, we didn't know that cancer cachexia is such a problem. So cancer cachexia is related to the metabolic syndrome, and if a person has cancer cachexia, their response to treatment is going to be worse, because they have a syndrome, they have a problem that's going to do muscle wasting. So even if they eat food, food is not going to help them generate energy to fight cancer or continue the treatment. This has been established in multiple studies, but there is no established way of detecting whether a person has cachexia or not. All people have been doing is looking at their BMI. If there is a more than 5% change in their BMI, they'll say that this person has cachexia. BMI is body mass index. So, but there are studies which show that if a person is obese, their BMI may not change, but they still have cachexia, because their muscles are being converted into edema and the weight is not going down. So this is one of the projects that we are doing. And again, we are trying to use multimodal approach. And we are processing radiological images, CT scans, as well as, to go quickly, I'm sorry, but as well as the EHR data, which is a patient's note, and try to use multimodal model so that we have a better prediction. This whole process is being built as a dashboard, and the dashboard will be available to the clinicians, so that when they come in the morning and they want to see a patient, this dashboard is going to tell them that this person may have cachexia or may not have cachexia, because this is their curve for BMI in the last 1 year. This is their curve of skeletal muscle index decreasing in the last 1 year. So please mark them as a potential candidate for cachexia and refer them to the nutritionist, so that they can in parallel start working on their nutritional side, and this which will actually come back and help those patients with their treatment. And that was the last slide. We are 8 members in the lab, and from postdoc to high school student, and yep, and that's all. Thank you so much. Yes, please.
So when you're building your models, have you considered how to deal with missing data for a particular subject? So if someone doesn't have a CT scan, for example, do you put that into your models?
Yeah, that's a very genuine question, and that's a very relevant question. That how do you deal with that? There are some statistical ways for data imputation. You can always go back and work on that. We can always do that, but what we have found is, and it's not based on some rigorous analysis up till now, what we have found is zero padding seems to work fine with us for these type of models. So that's what we are doing up till now, that if there is a missing data, we'll replace it with zeros. It's not the best solution. It's not supported by a rigorous investigation, but that's our strategy up till now.
Nice research, by the way. And I was wondering, like, about that multimodal training approach that you showed up in the slide. And at the end, you said like self-supervised learning.
Yep.
So for self-supervision, I'm guessing that you do some sort of data augmentation or data generation or something. And I'm wondering, like, how that, I guess, like, can you generate medical data? I guess, can you augment it?
So we can do an augmentation, which means that in certain cases, for example, if the tumor is on the right-hand side in the lung, we can flip that image and make it seem like it's on the left. But that's not going to work in some cases because of the human anatomy that is different in the right and left because of our heart. So there are certain ways where you can do the data augmentation. In the brain, we can do that. In certain cases, again, it's very application dependent. But for self-supervised learning, we do not need to have data generation capabilities. This self-supervised learning refers to the clip type of loss where we know that patient A, their modality 1 and modality 2, their CT and their MRI or their genetic data and their pathology data should be mapped closely, but patient 1 and patient 2's genetic data should be mapped far away from each other. So we don't need to provide don't need to provide a supervisory signal, but just based on the patient information and modalities, the model can figure that out. So that's a self-supervised learning task that I'm referring here. There are some efforts where people are trying to generate medical images using these diffusion-based models. Previously, people were using CycleGAN and other things. Up till now, there have not been a lot of successes in that.
I have a quick question. So is there a way like we can measure the confidence in the decision and the output prediction?
Yeah, there is no easy way, but that's a very important thing to do because if you know that your model's output is going to help somebody decide on somebody's treatment, which can save or not save their life. So we want to really build a decision. We want to really have a lot of confidence in our decision or output prediction. And you know that there is no easy way to do that except Bayesian, but Bayesian makes this thing very complex actually. These models are going to be highly complex. One way that we have found seems to be easier is ensemble approaches, where we can, for the final classification layer only, we have an ensemble of models where we can have maybe 4 or 5 or 10 different weights for the last layer only. And we can run that to get 10 different outputs and then just average them. This is not, again, the best thing to do, but this is a good starting point. Yes, please.
First of all, thank you very much for your presentation. Really, that's the best presentation I've heard so far about combining generative AI models with some specialized further developments. Great, really. Regarding this particular slide, I'm wondering how you distribute errors between different modality-specific models. How do you decide which should go into whatever imaging or clinical data or something else?
I'm sorry, I'm not able to
You
follow.
have a feedback.
Oh, so this
propagation of the-
this feedback, error propagation. Yeah, so that's a very good question actually. Up till now, so this is the diagram for kind of what we want to do. Up till now, we have this one only going here. That's it. We are not going back to this one because there's a lot more things going on here, which are based on domain knowledge actually, and we
There probably you have to get some data here.
Yes.
in between.
yeah, and that's not what we are doing. We should be ideally when we are done with the project, that's what we should be able to do that also. Yes, please.
Hi, first of all, great talk. My question is, for many types of cancer, there is a problem of overdiagnosis, where the diagnosed tumor may not have led to symptoms or could have resolved spontaneously. Basically, the diagnosed tumor couldn't necessarily improve all-cause mortality. So how do you think your multimodal models can help address that question?
Thank you so much for this question. It's a very important topic, and there are, and this is really important actually. One of my colleagues actually, their son they had the same challenge actually. I should not provide more details, but the overdiagnosis is a problem in cancer because cancers keep on, your body keeps on building those cancers and then destroying those tumors, building those tumors, destroying those tumors, because that's what our system does actually. So, but some of them will not go away, will not die. How do we know that we should, especially for example, in the lung, should we leave this nodule like this, or should we start treating it? And the treatment is really painful. Surgery or chemotherapy, it's painful. These are painful. This radiation also. There are active research areas where people are trying to do that, that we should be able to, given current image, we should be able to predict that whether this nodule, whether this small object is going to, small mass is going to develop into a lethal cancer or not. There are some brain tumors actually, which are left alone. If you leave them alone, they grow at a very slow rate, and people have already, maybe the person will be 80 plus years by that time. So you just leave that cancer there, leave that tumor there. There is no, we should not go and do anything. That's an active area of research. Hopefully, we will be able to build those models which can predict whether some given tumor is going to grow into something with lethal or it's going to stay the same. But right now, we don't have these type of models. I think they can do that because we are integrating information from radiology, from pathology, from genetics also. So hopefully these models will be more informative, more accurate than just using one modality. Yes, please.
Could you go to slide 24? Just curious about the LLM. Yes. So my question is are there any other metrics in to assess the performance of this LLM? Because I'm thinking conciseness of the generated response is not necessarily correlated with like the meaningfulness of the response,
Yep.
right?
That's again very interesting question. Thank you so much for asking that question, because that question has been coming back again and again. And when we presented this study at RSNA this year, last year, Radiological Society of North America, and the radiologists came back with the same question. do you really think that if you make it concise, it's more clinically relevant? No, that's not our claim. Our claim is that it has now less words. You as a radiologist have to see that if this helps you quickly review that information and do what you want to do. So it's not putting radiologist actually, it's helping radiologist with a small number of words. Ideally, we should be able to give some metrics, but right now our metrics are only radiologists actually who are willing to collaborate with us, and they can provide us some subjective feedback that yes, I find this more helpful now.
Sorry, follow up. Like, wouldn't like a complex diagnosis require the complex like explanation?
Yep, that's true. That's part of this. So there is no single standard that we are trying to achieve for all different reports. So there will be some reports where there will be no reduction of the words because all the words are required. Yeah, so that's and again, many things, as opposite to what I used to think, many things in medicine are very subjective. And that's why we see that people go to different physicians because based on their experience, they have different view of the same disease. That's why we see that certain doctor is able to diagnose something immediately, but certain doctors, they even despite the fact that they may have more experience, but they still could not diagnose a specific disease or specific case. So that's because everything is subjective, so we cannot enforce a unique metric or accuracy that this is what it is actually. So all of these things are help our physicians spend more time where human intelligence is required rather than working on something which can be actually a trivial task for dumb machine learning models.
So there will be more time for discussion in the lobby. So let's thank our speaker for today. And I mean, we will be having so we can ask more questions, one-to-one question.